Hello everyone, welcome to another Leetcode video. Today we're looking at the problem kth largest perfect subtree size in binary tree, which was question 2 in weekly contest 419. So the question reads that we're given the root of a binary tree and an integer k. We want to return an integer denoting the size of the kth largest perfect binary subtree, or -1 if it doesn't exist. And here we define a perfect binary tree as a tree where all leaves are on the same level and every parent has 2 children. So looking at this example here, we return 3. And we return 3 because these are all our perfect binary subtrees, all the ones that are labeled in black. So 1 is a subtree, 8 is a subtree, 5, 1, 8 is a subtree, 2 is a subtree, 6 and 8 are subtrees, 5, 6, 8 is a subtree, and 7 is a subtree. And these are all the sizes outlined down here. We see the kth largest, or second largest one, since we have k is 2, is 3 in this case. So we want to return 3 since that is the second largest tree. Let's take a closer look at this example and see exactly how we can solve it. So we're using the same tree from the example, and we're going to try to think about how we could figure out what the size of our subtrees are. So we want to use the same rules. So we want to make sure that every parent has 2 children and that our subtrees have the same height. So how do we actually figure this out? Well, let's take a couple examples. What if we have this tree here? What is just one node? Well, you can try to remember that just a single node is technically a valid perfect tree, but I'd like to think of it in a slightly different way. So if we come down here, we don't actually have children here. Let's just say that these are none, right? Well, what we can do is say, if we're at 1, I don't know if I'm a perfect subtree, let me ask my children. So we come down here, and if we ever see none, what we say is, I want to return 0, 0. And what does 0, 0 mean? Well, this is the height of my subtree, this first, and then this is the size of my subtree. And we do the same thing here. We return 0, 0. So how does this actually help us? Well, here what we can do is say, I'll get my 2 here, I'll get my left, and I'll get my right, which are 0 and 0. And then here I can actually check this, right? So I could check if they have the same height. Well, I see here I said that my first is actually my height, right? And I'll see that 0 does equal 0 here, so this checks out. But how do I check if I have 2 children? So I could either have 2 children or actually 0, right? This is saying every parent has 2 children, but this is actually not a parent because we have no children. And I could tell that, again, because 0 and 0 means that I don't have any children. So in this case, I could say, well, if my heights are equal and my sizes are equal, then in this case, I know that this is a valid subtree. So this is kind of the base case we're going to work on, where is if we ever see a none node, we're going to return 0, 0. So let's think about a slightly different case. So here, I have a tree that looks like this. I have these nones here. So here what I'm going to do is I'm going to return these 0, 0 up just like I did. So my left here and my right here is going to be 0, 0. I'll write that here. So I have a left and right of 0, 0. And what do I do here? Well, I see that, yes, my heights are the same, and I do have 0 children in this case, which is a valid case. So what I can say is, all right, well, I'm actually a good tree. So what do I want to do in this case? Well, I can basically pass this information up to my parent. And how do I do this? Well, the new height becomes whatever height I'm given, so 0 here, plus 1. And why do I do this? Well, I know that my heights are the same, and I want to tell my parent that I've checked my children, I know what the heights are, but I'm going to add 1 to this to account for this node as well. And then for the second value, I do a similar thing where I say the size of my subtrees are 0, but I'm adding myself in as well. So what I'm going to do is I'm going to return 1, 1 up here. So let's look at our subtree over here. Well, here I'm going to return 0, 0 from my right side. This is my left side. So here I actually see that 1 does not equal 0. So in this case, I immediately know that this cannot be a valid perfect subtree. And that also technically means that anything up above can't be perfect either. So in this case, I want to return negative infinity, negative infinity. And this is just a kind of symbol that we have found that our subtree is not perfect anymore, and we want to pass that information up to our parents as well. So we're going to use this methodology in order to figure out all our perfect subtrees. And as we go through, we're basically going to record these sizes if we find one that is perfect in a list. So we can just record them here. Say we have 1, 3, 2, 4, 7, whatever. Then at the end, we just basically sort this list, and we're going to return the kth largest value. So very simple. So the time complexity here is going to be O of n log n. And why is it O of n log n? Well, we have to go through every node, right? We're going through every node in the tree once, which is O of n. And the O of n log n comes because we do have n nodes, and at the end we're sorting them, which is an n log n operation. So this is plus O of n log n. But in this case, we just use the larger value. We can get rid of this. So our overall time complexity is O of n log n. However, there is another quicker way to do this. We can use a technique called quick select, which when you ever have these kth largest kind of problems, you can actually get that value in O of n time using quick select, which kind of works similarly to how quicksort works. I'm not going to cover that in this video because it's a little out of scope, and the O of n log n solution is perfectly fine for this question. But if you're curious on how you can do this in the most optimal way possible, I would definitely recommend looking up quick select as well. So let's hop over to the code and see exactly how we can solve it. So the first thing we do here is set up our sizes array, which is just going to hold all the sizes of the perfect trees that we find. Then we have our recursive function, and our base case, like we talked about before, is if our root is none, we're just going to return 0, 0. And this represents the height of the current subtree as well as the size of the current subtree. Then if the root is not none, we're going to get our left and right subtrees. And if they don't have the same height, we know that this subtree cannot be perfect. So we're going to return float negative infinity, which is just kind of a symbol that this is not a perfect tree and that we should not consider it as we think about all our sizes. Then what we do is we check again is if the values here, if the sum of all our values here does not equal float negative infinity, this means that we do have a valid perfect tree, and we should add that into our sizes array. Then at the end, we're just going to return the size of our tree plus 1 to account for our current node, plus the size of the subtree, which is the size of our left subtree, the size of our right subtree, and plus 1 for this current node. Then we call that recursive function. And then at the end, this is kind of an edge case where if we don't have enough perfect subtrees to actually have a kth value, we're just going to return -1. Then we're just going to sort the array, and then we return sizes -k, which represents the kth largest value in our sizes. So let's submit and make sure that it works. And it does work. So hopefully this is helpful. If you liked the video, please like and subscribe, and thank you for watching.